Hello everyone, let's start the new section. In the next two sections, we turn to the nature of the vector field itself. A complete description of any vector field requires the two properties of divergence and curl. We learned earlier in the electrostatics that Gauss' theorem gives the flux properties of the electrostatic fields. Gauss' law gives the relationship between the flux through the closed surface and the net charge enclosed by the surface. So, for magnetic field, what's the nature of its flux? First, let's look at the properties of the magnetic field lines. Following the previous method of describing electrostatic fields by using field lines, we can introduce magnetic field lines, also known as magnetic induction lines, to visually describe a constant magnetic field. This concept was created by Faraday. We stipulate that the magnetic field lines are directed curves, and the tangent direction of each point is consistent with the direction of the magnetic field B at that point. And a point P in the magnetic field on an area perpendicular to the field B at that point. The number of the magnetic field lines passing through is equal to the magnitude of the field point B. Thus dN over ds vertical. In this way, in the magnetic field line distribution diagram, the magnetic induction intensity B is large where the magnetic field lines are dense, and small where the magnetic field lines are sparse. From several typical magnetic field line diagrams, such as infinitely long current carrying straight line wires, circular loops, and solenoids, it can be seen that the magnetic field lines have the following characteristics. The first, a closed curve with neither a starting point nor an end point, including curves that stretch out to infinity at both ends. A second, interconnect with the current, obey the right-hand rule. The third, the magnetic field lines do not intersect. In the magnetic field, the number of the field lines crossing through any curved surface S is defined as the magnetic flux. As known in the figure, taken any area element ds in the magnetic field along the normal direction, the magnetic field line B passing through the area element is the area element perpendicular to the magnetic field B at this point. According to the above definition of the field line, the magnetic flux crossing through the area element is d phi m, which is a curve vector dot product of B and ds. Through integration, the magnetic flux phi m passing through the entire surface S can be obtained. If S is any closed surface, then the magnetic flux through S in the magnetic field is a closed surface integral. For a closed surface S, we take the normal n of the surface to be positive outwardly and negative outwards. When the field line enters the surface, the angle between B and the normal line n is acute, and the magnetic flux is correspondingly negative. When the field line leaves the closed surface, the angle between B and the normal line n is obtuse, and the corresponding magnetic flux is positive. Therefore, the magnetic flux is a negligible value. Since magnetic field lines are closed curves, a magnetic field line that enters one part of a closed surface must exit another part of that surface. Therefore, the net magnetic flux passing through any closed surface in the magnetic field is identical to zero. This equation is called Gaussian's law for magnetism, which is a basic law of the electromagnetic field. Compared with the electrostatic field, the electric field lines are generated by the electric charge. They always originate from positive charges and end with negative charges. Therefore, the electrostatic field is an active field, while the magnetic field lines are closed curves with no heads and no tails around the current. So, the magnetic field is passive. The magnetic field have no discrete positive or negative magnetic charges or monopolars corresponding to the positive and negative charges. Therefore, from the classical field theory, isolated magnetic monopolars do not exist. That's all for the section. Thank you for your attention.